In this video, we're going to look at the following physics work and energy problem. A skier approaches an 18-degree incline at a speed of 12 meters per second. She goes 12.2 meters along the incline before coming to rest. What is the coefficient of friction, mu? So first, I'm just going to label what I have. We have an 18-degree incline. This distance here is 12.2 meters, and we know that the initial speed is 12 meters per second. Okay, so what I'm going to do is I'm not going to solve this equation at first in terms of all of these different numerical quantities. Instead, I'm going to do it in terms of variables. So instead of 12.2 meters, I'm going to solve it in terms of d for distance. Instead of 18 degrees, we're going to use theta for the angle. And instead of 12 meters per second, we're going to use v for velocity. And m will stand for our mass, which they don't give us in this problem. So to start off, we know that this skier only has kinetic energy because we're going to call this our potential energy equals 0 point. Therefore, this 12 meters per second is all kinetic energy. So our kinetic energy initial is equal to 1/2 mv squared. Now, we can calculate our kinetic energy final. Actually, it doesn't require much calculation because the skier comes to a rest. So that kinetic energy final is 0. We already said that the initial potential energy is 0, but we can also calculate the potential energy final. Our equation is mgh. We have m, we have g. Now, they don't give us h directly, but we can calculate it. This here is our h, and we can calculate it by the distance traveled, we'll call it d here, times the sine of 18 degrees. So we'll call it mg times d sine theta. Okay. Now, we can't just use the conservation of energy approach that we're accustomed to, where Ke initial plus Pe initial equals Ke final plus Pe final, because there's a non-conservative force acting on the system, and that's friction. And we're trying to find the coefficient of friction. So let's calculate the work done by friction. We know that's going to be equal to the force of friction multiplied by the distance multiplied by the cosine of 180 degrees. That's because the friction force goes opposite the direction of motion. This cosine 180 will give us a factor of -1. That's why the work done by friction is negative. So I can rewrite that as negative force due to friction times the distance d. Alright, now let's break down this force due to friction. They don't tell it to us, but we know it's negative the normal force times our mu, our coefficient of friction, which we're trying to solve, multiplied by the distance. Now let's figure out this normal force. So imagine the skier is on this point here on the incline. The normal force is pointed in this direction, perpendicular to the surface. So what I'm going to do is I'm going to continue that triangle down here. Now we know that this vector here is the gravitational force vector, mg. Now this small triangle here is similar to this bigger triangle that makes up the incline, where this 18 degrees theta is this angle right here. So the question is, what is this normal force? Well, this magnitude is going to be the same as this one right here. So how do we calculate that? mg the hypotenuse of this right triangle multiplied by the cosine of theta. So negative mg cosine theta. Let me just change that to a capital M for now. And again, we're going to keep the mu and the d. Okay, so now we know that the work due to friction is equal to negative mg cosine theta times our coefficient of friction times d. So now we can set up an equation to solve for our coefficient of friction. We have our initial energy, which is our kinetic energy initial, 1/2 mv squared. Now we're going to have to add the work due to friction because this system here is losing some of its kinetic energy because of the friction. So it's going to become forms like heat, sound. So we need to account for that by adding the work due to friction. Since it's negative, when we add it, it's actually going to take away from the initial energy. So we have plus the work due to friction, and that's equal to our final energy, PE final, mgd sine theta. Okay, now I'm going to substitute in for an expression for the work due to friction. 1/2 mv squared minus mg cosine theta mu d equals mg d sine theta. As we can see here, there's an m in each term, so that can cancel out. There, the m's cancel. So we have 1/2 v squared minus g cosine mu d equals g d sine theta. Now I'm going to move the 1/2 v squared over to the other side. Negative g cosine theta, should be a theta here, mu d equals g d sine theta minus 1/2 v squared. Now we're going to divide by negative g cosine theta and d. So both sides we're going to divide by negative g cosine theta d. So our final expression for the coefficient of friction is equal to negative g d sine theta minus 1/2 v squared divided by g cosine theta d. Now this expression here means that it did not matter what numbers they gave you in the problem. You could just substitute them in right here. I've done the math and I plugged it in, and we get a final answer of a coefficient of friction equals 0.308.